to our next presentation, which is Idaho National Lab, another one of the national labs in the United States, and one that's close to Utah. So in many ways, we do feel that they're our national lab. And this is a pre-recorded session, so I'm going to turn the screen back over to Kathy, and she will run the video. Welcome back to the UMDC Defense Manufacturing Research Symposium. Our next speaker is from the Idaho National Labs. We are going to be talking about some of the programs that Idaho National Lab has in defense manufacturing, and also some ways that the Utah research institutions, academics, and companies can work and align with Idaho National Lab. In many ways, Utah considers INL our national lab because of the proximity. Rob O'Brien is going to be speaking with us today. Welcome, Rob. Thank you for joining us.
Thank you.
Fundamentally, Rob's research has focused on the development of processes and methodologies for advanced materials, and in deploying these advanced materials and systems in extreme environments. So let me turn it over to you now, Rob. Why don't you share your screen? And we look forward to your presentation. I'll come back and we can ask some questions later.
Wonderful. Thank you. Well, it's a pleasure to be with everyone this afternoon. Again, to share our interest in advanced design and manufacturing for extreme environments. And also to give a background, a brief background on what Idaho National Lab's fundamental missions are and the mission areas that I think can be seen as opportunities for collaboration and connection to the broader industry base. So with that, I'd like to jump in to give that small overview of where Idaho National Lab sits and a little bit of background of how many employees we have. Roughly 4,900 employees that cover a variety of roles and functions across a number of mission areas. We have 5 mission areas at INL that we'll talk about in just a moment. 5 mission areas at INL. Idaho National Lab can be seen geographically in the eastern Idaho Snake River Plain. We are roughly 890 square miles of what we would say is lab space. This is open land and facilities that allow us to perform very unique mission support functions for both the Department of Energy and our collaborators in a number of agencies and sectors. We have, if we think about business volume, we were in FY19, we were $1.35 billion business volume. And I think there's a lot of excitement in the energy sectors and a lot of opportunity for that business volume to grow along with our industry collaborators and partners. We have some statistics on the right-hand side. We have 4 operating statistics on the right-hand side. We have 4 operating statistics on the right-hand side. We have 4 operating statistics on the right-hand side. We have 4 operating statistics on the right-hand side. Years. We've been here as a lab for just over 70 years. There are 17.5 miles of railroad, 40 miles of primary roads within the complexes themselves. And a lot of opportunity with infrastructure for testing infrastructure. We have 7 substations and interfaces for power grid, and in addition, 112 miles of high voltage transmission lines. So this is certainly relevant for our interests in supporting cyber security awareness and testing of this infrastructure and critical infrastructure. As another note, we have our own support infrastructure, including fire and EMS, and we have 3 fire stations at the Idaho National Lab. So a lot of great capability and support infrastructure that can enable a number of mission areas R&D. Idaho National Lab is not a sole lab. As we know, we're one of 17 Department of Energy national laboratories that are nationwide. Idaho National Lab in blue here, we fundamentally serve nuclear energy. Idaho National Lab in blue here, we fundamentally national and homeland security mission. Nuclear energy. Idaho National Lab in blue here, some of those defense applications as well, and some opportunities later throughout this presentation where we perform research. But in general, the work that we do across the labs is interconnected. The programs the labs we support is interconnected. Bridge across many other the labs we support is interconnected. Bridge across whether it's is interconnected. Bridge at Oak Ridge National Lab in advanced manufacturing is the fundamental emphasis in this talk is focused. But also other energy applications that we explore together with other parts of the complex. So our fundamental mission at the Department of Energy National Labs is to support energy science, national security, and environmental stewardship. And the work that we do at INL is certainly no different. We support unique and multidisciplinary goals and science exploration that typically bridge beyond the scope of university and academic institutions, really to support research in both energy and national strategic priorities. Of course, tied to that is developing critical infrastructure and capabilities from a science and an energy perspective that really require government support, and the national labs help enable that sort of research. Within Idaho National Lab, we have some fundamental missions or primary mission areas. These are nuclear science and technology, national and homeland security science and technology, and energy and environment science and technology. And the cross-cutting nature of some of the infrastructure that we have supports all of these mission areas, both the nuclear science and an energy environment, and then in addition, the work that we do in national and homeland security in support of branches of the Department of Defense. If we think about advanced manufacturing, we see advanced design and manufacturing as an enabling approach to design and manufacturing as an enabling approach serve both in design and manufacturing as an enabling that enable approach serve both in design and manufacturing as an enabling also enable broader industry competitiveness both nationally and internationally. And the work that we're doing really focuses on the fundamental process discovery, and then accelerating the discovery and enabling refinement and ultimately leading to utilization and deployment in the industry sectors. We're looking at clean energy technologies, methods that reduce carbon, that allow competitiveness for industry, both from a sustainability perspective and economics perspective. We work in the areas of secure design manufacturing, enabling the conjunction between cyber awareness, cyber engineering, and sustained manufacturing. And the sectors that we look at are, of course, tied to our mission areas. So nuclear, energy, space, and defense are primary areas of interest. Examples of areas that we do in advanced manufacturing. Examples of areas of additive manufacturing. We see additive manufacturing as a method for controlling feedstock, for controlling composite makeup of new advanced materials. We also look at the conjunction between methods like additive manufacturing and steps and processes that can finish a material or assemble a system. And so we include in that other efficient manufacturing methods, such as direct energy processing and electric field assisted sintering and joining methods as examples to access some of these materials for harsh environments. So our initiative was set up a little over 2 years ago to engage in advanced design and manufacturing for extreme environments based on our interests areas and also the mission areas of the national labs. And so we established an initiative that is based on 3 pillars: process discovery, the initial discovery of a manufacturing method or material system. And then we have a second pillar that is focused on secure digital design and manufacturing. And our third pillar is based on intensification scale-up, that is looking at tech transfer and enabling the utilization of the discoveries that are made in the early stages, utilizing the design methodologies that are developed, and then putting them to practice to enable competitive manufacturing processes. So within the initiative, of course, the 5 directorates that the lab has mission areas in. On the left-hand graphic are some examples of systems and components that we develop manufacturing technologies for. And around the outside, you'll see the areas of interest might be nuclear fuels, of course, focused on our nuclear science and technology interests, ballistic protective materials, hypersonic materials, and electronic systems are to note, and I think relevant to the defense interests. Within the pillars that you'll see in the central graphic on the outside, process discovery, secure digital design and manufacturing, and intensification and scale-up, we also engage in, of course, subcategory activities that support those pillars. And each are equally important in terms of execution and manufacturing for harsh or extreme environments. Everything from proof of principle testing, so experimental interrogation, verification and validation of modeling and simulation methods. This is a very important step when we're developing materials from first principles or from theory. It is important to both perform verification of the models and then perform unique types of experimental interrogation of materials or manufacturing processes using in situ experimentation and instrumentation. That goes hand in hand with process-informed design, which is what we see as a methodology set to bridge between taking a design that is for a specific application and having a distilled or understood methodology for manufacturing a material, designing that part both to work within that process, but also modifying the process to make a microstructure, as an example, that is of interest or relevant to that design application. Cyber engineering goes hand in hand as we design manufacturing spaces, as we design the equipment and apparatus, as well as the overall design space, what would traditionally be bridged into an enterprise environment that could be gapped from the manufacturing environment. We see that cyber engineering is an essential part of our future in manufacturing. We see that there is a lot of opportunity both to develop approaches, but also to ensure product surety and ability to deliver on a mission by tying cyber engineering from first principles development. And that goes hand in hand with automation, plant design, pilot demonstrations, and of course, there is an element in digital twin tied with modeling and simulation to all of the discovery phases. So all of these items that we mention here are very much interconnected and play an essential role in our initiative. If we think about capabilities at INL, and then I'd like to also comment on how this touches the rest of the complex. We have some unique capabilities. The capabilities that have been developed and invested within INL stem from both programmatic interest and internal research and development efforts, such as IRAD-like or what we call lab-directed research and development projects and programs. The infrastructure that has been developed has certainly touched a broad number of areas that you'll see here in advanced manufacturing. And the infrastructure is not in one individual location. We actually have capabilities that are assisted both in radiological environments, so extreme environments from the nuclear science perspective, but also in the cold or secure environments, such as in the EES and TR energy and environment science and technology, or our national and homeland security sections. So we have a number of capabilities in additive or 3D printing that tie to nuclear fuel systems components. It ties to systems, thermal engineering components, thermal management systems, so there are some common sort of sistered capabilities there in additive manufacturing, both in what we call our research and education campus, which is in the city of Idaho Falls, and then some 30 miles outside of the city at our materials and fuels complex. That is the MFC symbol that you see here with some of the purple capabilities. We look at materials and, of course, looking at how materials perform in extreme environments. We're interested in performance in nuclear reactors. So our advanced test reactor is a capability that we engage to test performance. At the advanced test reactor, we also have some manufacturing capabilities that support the primary mission there, which is enabling irradiation testing. Back at the materials and fuels complex, there are some capabilities to grow single crystal materials that are of interest in terms of understanding material performance, eliminating thermal transportation convolution or complications that we would see with polycrystalline materials of a new type of material. For example, trying to understand thermal conductivity can be challenging, especially with phonon scattering. And so using single crystal growth methods to grow materials of interest and then find the fundamental heat transfer properties, we can connect those back to our modeling and simulation capabilities. Over on the right-hand side of this graphic in yellow, you'll see the nuclear science and technology capabilities are very complementary. Moose is a box that, this is a modeling and simulation framework that has been developed over the last 10, 15 years at Idaho National Lab and is used throughout the DOE complex and within academia and industry partners to streamline simulation of complex physics. And there are a lot of capabilities there that are being developed for advanced manufacturing, a suite of tools that can probe and estimate the performance of a manufacturing approach. Equally, in-pile instrumentation, as we talk about material performance in test, embedded sensors are essential. Embedded sensors that work within the manufacturing process, sensors that work within operation in a nuclear reactor and other extreme environments. So there are a lot of cross-cutting and complementary capabilities that you'll see here across the INL complex that really assist. Everything from material manufacturing, coatings, assembly, joining, and overall testing as systems or components. I think there's some very exciting capabilities that can be brought to bear on a whole number of very different problem sets. One area to note is our Center for Advanced Energy Studies, or CAES. This is, there are some unique capabilities there in microscopy that are more open access for academic institution partnering, and that includes everything from process chemistry, sample prep, and a microscopy suite with state-of-the-art instrumentation that is accessible to any institution that would like to participate. Mentioned the connectivity to the rest of the National Lab network. We work closely with colleagues across the National Lab complex, especially focused on advanced manufacturing. Our friends and colleagues at Oak Ridge National Lab, the manufacturing development facility, certainly have a lot of complementary research, especially in the additive advanced manufacturing realm, and certainly we have some very complementary work at INL. We partner with other parts of the complex to solve mission area challenges and manufacturing challenges. And we have collaborations with a number of other national labs, including Ames Lab, Lawrence Livermore, Kansas City plant, and NETL. And examples of those can be seen in the Critical Materials Institute and the Remade Institute. I'd like to talk a little bit more about our research and education campus and highlight some deeper connections and opportunities with capabilities. So our research and education campus has a fundamental role in advanced manufacturing. This is to enable advances in energy and harsh environment materials development by engaging in our process discovery phase exploration of materials that's coupled with modeling and simulation methods development, as well as utilization. And I like to call this distilling process science from discovery through intensification to deployment. So this is both the front and back end of the discovery phase. Some of the capabilities to talk a little bit more, I think these are areas for collaboration. Spark plasma sintering, we'll talk a little bit about that in a moment, but there's some very unique capabilities that spark plasma sintering or electric field assisted sintering can bring to manufacturing materials very rapidly and affordably. We have capabilities in trusted electronics and instrumentation manufacturing, being able to go from chip to finished electronic component in a secure environment is very attractive. And we'll give you an example towards the end of this presentation where this has been very useful most recently. We have capabilities in additive, as we mentioned, lens manufacturing, filament deposition methodologies, plasma jet, binder jet, and also digital light processing are methods that are being developed for a number of applications. Roll-to-roll, one of the challenges in production of hydrogen is being able to manufacture fuel cells that are efficient or electrolysis cells that are efficient, and roll-to-roll methodologies coupled with some of our additive and EFAST methods are certainly of great use and interest there. We have a number of capabilities in welding, laser welding, for example, and annealing, surface coatings to act as barriers for corrosion resistance. And then on the end of life side, we have a lot of work that is focused on e-waste recycle and polymer and metals recycle. Some examples of some of the in-pile instrumentation that we develop in embedded sensors might include systems like this. This is the micropocket fission detector that allows us to measure reactor power. And as you can see by the size of this compared to a penny on the right-hand side here, you can see that the stack of individual cells can give us a spectral analysis of reactor power, so both fast and thermal neutron spectrum. This is very useful for reactor engineering, but it does highlight the capability for microelectronic and microsensor development. At our materials and fuels complex, which I mentioned is some 30 miles outside of Idaho Falls, we see the function of advanced manufacturing here as bringing to the table a number of unique capabilities and very unique infrastructure that allows us to enable advances in nuclear fuel systems components. It allows us to develop irradiation science experiments and ultimately reactor technologies that are improved over the current state-of-the-art processes. And we do this by adapting and analyzing new or novel techniques for manufacturing. You'll see this that the facilities are certainly in a remote location and house very unique both processing and controls, environmental and engineering controls, to allow a number of materials for extreme environments to be probed. Some examples of capabilities here again focus on electric field assisted sintering, radiation science development, manufacturing of experiments that go into reactors, and also other tests, including ballistic testing. Single crystal growth, we have a number of powder metallurgy techniques that are available for research, and then of course advanced coatings and more advanced joining and welding techniques. I did want to talk very quickly about electric field assisted sintering. We see this as a very exciting method that can support manufacturing materials for harsh environments. This is a technique that is akin to traditional hot press powder metallurgy techniques that can turn powders into solid compacts. And these compacts can be complex in geometry. They do not have to be right cylinder. They can be a number of different complex shapes, including curvature and internal facets that allow operation in the desired environment. This technique uses kiloamps of current, but for a very short amount of time to process material into a solid. It's typically performed at low voltage, some 20 volts or less of DC, but it is kiloamps per square centimeter in current density. It can be a continuous DC current that is applied to a powder inside an electrically conductive net shaping tool, or it can be a pulse DC current. So there are a number of approaches that give you an average temperature, but ultimately this technique is performed. It can be net shape, done in a much shorter amount of time, therefore saves an incredible amount of energy over traditional powder metallurgy techniques. And equally, the energy saving is felt because this process technique is performed at 40 to 50% of the melting point of the materials, as opposed to 80% of the melting point. So an incredible reduction in temperature can be achieved because of the nature of the electric field and its influence on sintering. Some examples of things that we've worked on and development of electric field assisted sintering at Idaho National Lab. We started some of our interest and research in spark plasma sintering in 2007. We had some internal research and development. This allowed us to develop infrastructure that you see on the bottom left side. Was a small electric field assisted sintering system, roughly 1500 amps of power supply and relatively small hydraulic press. And then over the years, we've developed a number of other infrastructure and capabilities that enable EFAS development at different scales, more akin to a bench scale production effort. So between 2011 to 2015, we developed a very unique capability that had an integrated glove box and one of these EFAS systems that could press not just inert materials, but also radiological materials. So we had all of the engineering controls in place to handle some harsh environment materials. And since then, this system has supported a number of industry partners and mission areas, including NASA, projects for Aerojet Rocketdyne, and other national and homeland security mission areas in both nuclear and reactive materials, and also hard ceramic materials. So incredible capabilities. Since then, we've deployed these systems at the materials and fuels complex and grown capabilities in our research and education campus. Some examples include hard ceramic materials, complex net shapes in those, also thermoelectric materials for harnessing heat for energy recovery, advanced accident tolerant fuels, corrosion resistant materials, advanced isotope target, so isotope production target for medical applications, and then also some fuels and materials for ultra high temperature reactors. And what you'll see in the center of this picture is a stack of some fuels, and then the hexagonal shape that you see in the center with flow channels. This represents space reactor fuels that are of great interest for enabling exploration and national security missions of the future. Some examples of where that work has been irradiated. In 2019, we performed the first irradiation of advanced manufactured nuclear fuels inside an additively manufactured capsule at our treat reactor that had just come online just a few months prior. This was a reactor built in the 1950s and was mothballed in 1994. We recovered that system in 2018, and in June of 2019, we made this world first attempt to irradiate, and these fuels have been tested at 3000 Kelvin, and they're relevant to some of the advanced space reactor systems. As we think about growth and where next, when we talk about industrial deployment and utilization, we are in the process of finalizing construction, the world's largest true electric field assisted sintering system. This is an 800-ton press, 150,000 amp current system capable of sintering 24 to 36-inch diameter components and stacks of materials to net shape, or to join and diffusion bond very complex, hard to join materials. This includes a number of materials for our national and homeland security mission areas, including super hard, ultra incompressible materials, transparent materials, and ceramics. Again, in the nuclear fuels area, looking at mass production of nuclear fuel systems components in materials that are very difficult to manufacture using traditional methodologies. There are interests in supercapacitor, solid state energy storage, and heat exchange technologies, as well as solid oxide electrolysis cell technologies for hydrogen production and fuel cell operation. This system is now in the final throes of completion of its installation. This picture is dated from October. It's not quite complete in this picture, but you get a sense of the scale with some of our staff here stood to the right-hand side of this piece of infrastructure. We performed the first power tests in the system on the 8th of March this year. So it's very much a process and system that is nearing completion. But this will be an established backbone for automation controls, a test bed for cyber engineering. It will allow us to test a number of materials that are relevant to both the defense and energy sectors, as well as other industry areas as well. I did want to highlight some of our support in the under the CARES Act and to highlight the cross-cutting capabilities at Idaho National Lab and ability to adapt to new problem sets and new challenges. As we've all been facing with the COVID-19 pandemic, there is a lot of challenges in the both the supply chain, also in sustainability and also resilience in manufacturing. And we have demonstrated a number of approaches to continue operations, but we've also supported broader industry sectors that Idaho National Lab had not traditionally supported, specifically in the medical manufacturing areas, in collaboration with a total of 16 labs focused on the National Virtual Biotechnology Lab. And Idaho National Lab has led 6 laboratories in developing novel ventilation techniques and transformative ventilation technologies that can support the medical sector and patients recovering from COVID-19. In doing so, we've developed a number of low cost, affordable, and non-competitive for supply chain components, ventilators that could be deployed world over. Our colleagues at Lawrence Livermore National Lab had an emergency use agreement and spun out a product through an industry partner that is now taken to an international market. We have supported an Idaho company from Coeur d'Alene, Idaho, Percussion Air, in modernizing electronics and manufacturing approaches to allow mass production of some of their technologies in what is known as intrapulmonary percussive ventilation, which has had a number of use cases, including in DoD missions, both nationally and internationally, for life flight and field hospital ventilation. We've looked at transformative sources of oxygen generation to eliminate the supply chain, using air to concentrate, using additive manufacturing to concentrate air into pure oxygen or purify the oxygen for feeding ventilators. In addition, we've supported an Oak Ridge National Lab led effort in a collaboration that is developing PPE or respiratory PPE technologies, including standing up testing capabilities that are in accordance with the NIOSH standards to allow us to rapidly screen candidate materials for filters. And additionally, INL has supported in data analytics activities to look at supply chain and connecting that to virology modeling to allow us to predict where the needs are going to arise for system deployment, and also looking at supply chain gaps and being able to support industry in closing those gaps. So in summary, Idaho National Lab has a lot of interesting manufacturing capabilities that can support a broad industry base, including defense and energy sectors. It's fair to say that we have a high consequence, critical path supply chain and component manufacturing set of activities and challenges. And these are certainly analogous to sort of broad industrial and defense activities. We have existing advanced digital design and manufacturing capabilities that can be exercised to address a number of supply chain challenges and problem sets, both for DOE, can be used for DoD, NNSA, and other industrial commercial needs in research and development. we believe that cyber-informed design and secure manufacturing is going to be essential at every step and in every installation for industrial and commercial activities. And the capabilities and the collaborations that we have to offer, both from an expertise and infrastructure perspective, can be leveraged for a number of potential projects and programs, and we can be seen as a test bed under the AMO Cybersecurity Institute, the CIMANI, that was recently awarded, but other work for others and strategic partnership projects are also possible to be engaged in these frontiers. So with that, I'd really like to thank everybody for the time, and certainly my contact information is here at the bottom, available, and would be very happy to connect you with our colleagues across the lab if there's areas of interest that you would like to discuss offline, and also happy to field other questions as they arise. So thanks again for the time, and enjoy the rest of the session. Thank you.
Thank you so much, Rob. What a great presentation. It was comprehensive, yet very much focused on the Utah defense manufacturing community, which brings me to, so how does INL seek out or find academic and other research institutions like those of ours here in Utah to partner with?
We certainly are positioned to respond, to answer questions and solve problems collaboratively. Our doors are open and certainly receptive at any time to field those questions and areas of interest. We often see opportunity through both the Department of Energy and other areas for partnering. So with their funding opportunity announcements that are through the DOE exchange websites or other branches of federal government funding opportunities that we can partner with. We also have the ability to partner to solve immediate problems that may fall outside of those funding opportunities through our strategic partnerships projects and work for others or creative processes.
And you may not know this, but one of the major focuses for Utah Defense Manufacturing Community programs is workforce. And part of workforce is apprenticeships and internships. Does INL have that kind of a program for internships or apprenticeships?
Absolutely. We have an annual and an ongoing internship program that can be at any point throughout the calendar year. We actively encourage partnership with academia and encourage students to come participate in internship programs that typically run through the summer. Although examples include longer term internships for placement of graduate students at the National Lab capabilities to engage in exercising work that is in support of their PhD or master's theses. So there's a lot of opportunity there from that respect. But we equally value the talent pipeline. Solving the energy challenges cannot be done by building infrastructure. It's a combination of growing expertise and the capabilities together. And so we're very much interested in collaborating and growing that talent pipeline together, both with industry and academia.
Yeah, and the students certainly come at these problems with a very different perspective that is refreshing and can present new and unique opportunities. Well, thank you very much. The UDMC will follow up directly with INL and see if we can establish a formal relationship for some of these programs. Well, again, thank you, Rob. I appreciate your time, and thank you for your contributions to today's symposium.